And so you might ask yourself right now, after seeing the last two videos, how the heck do I know what's happening with one of my qubits if I have like say even just five, right? That's just a lot. If I have five qubits and I have a messed up, like I have like a long algorithm I'm building, and I'm doing different things with it, and let's see, and I'm just putting random stuff, right? So, but let's imagine we have like a fancy thing going on here, and then basically now you've got a bunch of stuff that's entangled, and so you're you maybe need to use so first of all you will see what you will see that a lot of people talk about is they talk about quantum registers as uh, in contrast to quantum beads or qubits. And I think basically what people mean by these is a qubit is a qubit, and then a quantum register is just a group of qubits in your system. So the reason you use quantum registers instead of quantum beads is because as a naming is because if you're doing a calculation like you want to build a circuit that adds a plus b, then you're going to have a, it's kind of like a potentially large number, so you need more than a qubit to represent it. So you're going to pack three qubits together and you're going to say that's my register a, and you're going to pack three qubits together on the other side and say that's my register b. So people talk about registers, but don't let yourself be confused, because those registers, they don't have to be necessarily totally isolated. And what's more, if you make, as soon as you put them together and you're making a circuit by messing up with both of them, you will for sure create entanglement. You will for sure those qubits will get entangled. They will get it will be messy. So the thing is, how do you know what's the state of sometimes in those in you want to make a circuit where you're like, okay, I do a plus b, and then I will do something else with a, right? So but you want to know what's the current state of a. But it's complicated. You cannot see really here what's the particular. It's complicated to see what's the particular state of. Let's say maybe qubit 3 and 4 is maybe one register for me, that I'm using for something concrete in this example, right? So I don't know. Let's say that is one register and that's another register, and then that's like a qubit that I'm using for like is an auxiliary qubit that I'm using for something else. I don't know, just making it up. So you want to know really what's the substate of what's the state of that system, of that subsystem, ignoring everything else. And then, as I already said a couple of videos ago, you cannot just simply look at the circuit and say, oh, I know. I mean, if you have a small amount of qubits, like one or two, you can probably easily do that. But if not, that's complicated. So there's a tool for that, which you have here. It's called a density matrix. See if that renders. That's fancy, huh? It's a nice one. So the density matrix is basically another way to represent your state. And I'm gonna make it smaller right now because that's gonna be that's too complex to calculate at this stage. But the idea is, this is something that tells you about all the different relations and correlations between the different qubits in your system. Check out, I have a list where I talk about the density matrix and I explore a bit more because I was learning about this recently as well. So feel free to check that out for all the details. But the idea is, your diagonal items are the same as your probabilities that you will see in the measurement probabilities here. Takes a little bit, exactly, because there's a lot of qubits. But what you can also see from that matrix is, and let me maybe get rid of some of those. I'll just make a smaller example. Let me clear that. I'll make a small example because it's going to be easier to understand. So I'm making a small example. It's cute. It's disappearing. 5 qubits is already quite a big effort, I see. What am I doing? So let's just make a simple one with 2 qubits. It's simple enough. I mean, you don't need a density matrix for that, but the idea here is, if you're gonna do something like that, maybe a Y and maybe a Z. I'm just playing with the different ideas. Density matrix. So you've got that thing here, right? So basically, there's like a complex part, because if you remember well, in the very first videos I mentioned that this is about complex numbers. I mean, the phase and the amplitude, they are both like connected, and then you can, so the phase especially because it's circular. Um, it, it, it's represented mathematically with complex numbers, with imaginary numbers. You might have heard them as well, like these. But this is nothing to worry you about. To worry about is just you have the density matrix separated in two to make it easier to visualize. But in this case here, this is empty. So the idea is you can run something called the partial trace, and that's maybe a little bit of it sounds mathematical, but it's just a trick. Like if you add this plus this, I have to keep I have to keep. So here is like you have the trick. So yeah, it's really you don't have to do this by hand. I guess there are tools that allow you to do that. So you can, in theory, get that matrix and then get this. Um, get this for you. So this allows you to what have I done? Click here. So basically, if you add those components, then you get another matrix which is smaller, which is this plus this plus this plus this, and this matrix tells you what's the state of your subsystem. For each column is one qubit. So, but this is if you want to be able to read this matrix. Here, you will have to get your hands on a little bit of the mathematics behind that. So I'm just so you know. This is just so you know that you can, if you get to the point where you really need to know what your subsystem is doing and what a subsystem is made of, independently of the rest of the system. That's a tool you can use, but you need to get your hands with your hands dirty with a bit of the mathematics to do that. It would be cool maybe if you could have here some integrated tooling that would allow you to tell you right away what's the state of a subsystem. But it's probably something that maybe the IBM guys will add later. I don't know. We'll see. It's definitely a useful tool to know about. Definitely.